Hello and welcome everyone. This is Manish from Skill Level India. In today's session of geometric dimensioning and tolerancing, we are going to discuss most important topic in GD&T, which is circular tolerance, circular runout and total runout. Okay. So in this session, we will discuss about runout, both circular and the total runout. First, we will start with the circular runout. Okay. So what is circular runout? Circular runout, basically it is also called the radial runout. Okay. So here is a example of a drawing. I have taken one example over here. Okay. So before going into the example, first of all, whenever we give a circular runout, it should have a datum. Okay. So it is related to the datum. So whenever we are using the circular runout, this is the symbol of circular runout. Okay. So whenever we are using this symbol inside the box in the first compartment of the feature control frame, that means it is a circular runout. Okay. In this, the maximum material condition and the least material condition are not applicable. Okay. So runout is how much one given reference feature or feature varies with respect to another datum. Okay. When the part is rotated 360-degree around the datum axis, it is essential to control of a circular feature or and how much variation it has with the rotational axis. Runout can be called out on any feature that is rotated about an axis. Okay, what does this mean? We will understand in a detailed manner. So whenever we give circular runout, it should have a datum. So first of all, whenever we are giving circular runout, it should always has a datum. So datum is a must because it is a related feature. Whenever there is a related feature, it we have to take datums. Okay. So always the datum should be a regardless of feature of size. Why it is regardless of feature of size? Datums only. We cannot apply the maximum material condition or the least material condition, or we cannot apply the maximum material boundary or the least material boundary and to the datums. Okay. So here we cannot apply the least material boundary or the uh, maximum material boundary over here. Okay. So second thing is this is a circular runout. It is a two-dimensional entity. Okay. So circular runout, I will write it down over here. Circular runout is a two-dimensional 2D entity. Two-dimensional entity. Okay. Why we are considering that two-dimensional entity? Because whenever we are checking the part, okay, so we are checking at only one plane. Okay, so at let's say this is a circular plane. So we are checking at only one plane. Okay, so this is the one plane. If we are taking it from the perpendicular, let's say this is the perpendicular plane. So only at from the dial indicator, putting dial indicator, rotating this part and checking only at this circular profile. Okay, not over the length. So for the circular runout, we are only checking for one plane. Okay, so which it means it is also applies to a plane, single plane which is perpendicular to the datum axis. Okay, so this plane is always perpendicular to the datum axis. Okay, so in this case you can see that this is perpendicular, this plane is perpendicular to the datum axis. In this datum is considered because I have taken primary datum over here. So we have taken this primary datum as the datum axis. Okay, so this is taken as a datum axis. And this plane, this circular profile over the part, this circular profile at one plane is always perpendicular to the datum axis. Okay. So if you want to check the radial runout or circular runout, it is independent. You have to take it n number of times. Okay. So if we want to check multiple times, so let's say first we will check at this plane. One reading is coming. Then we will check at this plane. One reading will calculate. Then we will check at this plane. And multiple times we have to check over the length. Okay. So multiple times we have to check the circular runout because it is two-dimensional entity. Okay. So towards the length of the cylinder. For checking this circular circular runout, what is the most important thing, that when you have the drawing like this, whenever you have a drawing like this, I will erase all the things. Okay, like this, the meaning is, when I told the cylinder, this small large cylinder, okay, I get the datum axis. So when we hold, let's say there is a V block, okay, let's say there is one V block, and we have kept this part onto the V block, okay, this large part. So this large part is kept onto the V block. And when we rotate this part, okay, so when we rotate this part, the axis, the axis is used as the datum axis. Okay. So the datum, this is when we hold this part from the air and rotate this part from the datum axis. Okay. So I get the datum axis at this condition. When I put the dial indicator on the second cylinder like this, when we put the dial indicator on the second cylinder and then rotate the component, the full indicator. Okay, so this is a dial indicator. Let's say this having a there is one dial indicator. If this indicator, this pin is rotating, this pin is rotating 360-degree. Okay, or the movement value should be equal to the 0 point less than 0 0.1. Okay, if it is rotating, so which is given in the feature control frame. Okay, it is 0.1 mm in this case. So if it is rotating full, then we are considering. If it is not rotating 360-degree, means it is less than the 0.1 mm. So it is acceptable. Okay, because the tolerance which we have given is over here is 0.1 mm in the feature control frame. Okay, so now as I said, this is the two-dimensional entity. The tolerance zone for the radial runout is two coaxial circles which are perpendicular to the datum axis. Okay, so there are two coaxial circles which are perpendicular to the datum axis. Apart from this, we call radial runout as composite tolerance. Why we call this as composite tolerance? The question arises that why we called it as a composite tolerance. Because in this you can see, because it controls form, it is also controlling orientation, and as well as it is also controlling the location. So that's why it is called as composite tolerance. So here, what we are getting is circularity. Okay. So while rotating, we are checking the circularity of the cylinder with reference to the datum axis. Okay. At the same time, location of the center of the circle. Okay. Center of the circle and perpendicular plane coincident with the datum axis. Okay. Coincident with the datum axis. Which is nothing but the location. Okay, when we convert this into a total runout, let's say, first of all, before going into the total runout, I will show you the measurement. Okay, so circular runout measurement. Runout is measured using a simple height gauge. Okay, so let's say this dial indicator is fixed on the some height gauge of on the reference surface. The datum axis is controlled by fixing all datums points and rotating the central datum axis. Okay, so this part, let's say we have placed this part onto the V block. So this part is fixed and the axis, datum axis is logged. Okay, so what has happened, that the circularity of the cylinder with reference to the datum axis, at the same time location of the center of the circle at this perpendicular plane. Okay, so coincident with the datum axis, which is nothing but the location. Okay, so here you can see that this is the dial indicator, and if this dial indicator is rotating 360-degree, okay, it means it is considering 0.1 mm. Okay, and if we have given 0.1 mm as the in the feature control frame, okay, let's say 0.1 mm with datum A. So means it should not rotate 360-degree. Okay, if it is rotating, then we are out of circular runout. Okay. So the part is usually constrained with V block. So here V block, we constrained this part, or we kept this part onto the V block or a spindle on each datum that is required to be controlled. The part is then rotated around the axis. So now this part is being rotated around its axis. So this is the axis. So at this axis, this part is being rotated, and when it rotates 360-degree, this dial indicator dial should not move 360-degree circle. Okay, it always bubbling between 360-degree only. Okay, so the variation is measured using the height gauge held perpendicular to the part surface. As long as the gauge does not vary by more than the runout tolerance, the part is in the specs. Okay, let's say if I am talking about, if I have given the here 0.2 mm, means this dial indicator should rotate 2 times. If it will rotate more than 2 times, then only it will call out of the circular runout, that the runout is out for this single profile. Okay, you can see it is the perpendicular plane. Okay, so this is just a perpendicular plane, and this is why this is it. This is because it is called 2D entity. Okay, so now I think you should know that how we check that the circular runout of the part. Okay, now we will move on to the next part, which is total runout. Okay, what is different between circular runout and total runout? I will tell you. So total run, first of all, symbol, same sim. This is the symbol of the total runout. We use like this in the feature control frame. Total runout is how much one entire feature or surface varies with respect to the datum when the part is rotated 360-degree around the total axis. Okay. So in this, we are not checking only at one point. We are moving the dial indicator throughout the length of the part. Okay. So in total runout, we are not checking at only one point. We are checking the whole length, through whole length, total length. And we are moving this dial indicator at over the length, and we are checking that it is the whole length is under the 0.1 mm of tolerance. Okay, if the dial move more than 360-degree over the length, over the whole total length, that means that it is that it is out of the tolerance. Okay, so total runout controls both the amount of the variation in the surface. So it is just controlling the amount of variation in the surface. Okay, let's say if surface is like this. Okay, so it is also controlling the variation. So this is the variation. This variation always be within the tolerance. Okay, in the axial dimension, both radial variation and axial variation. Okay, so both the things in this radial variation, because the total length we are measuring, and the axis variation. Okay, axial variation where the axis is should be checked. So in this, we are not only checking the axis of this part, but also the radial direction. Okay, and held within the tolerance. So total runout is usually called on a part that is rotated about an axis where the entire surface is critical. Okay, so let's say if this whole surface is critical and we need to check this surface that it is within the tolerance zone or not. So we will check with the help of total runout. Okay, with the help of example, we will understand this. Okay, so total runout is measured by fixing the datum feature, typically an axis, and rotating the part along the rotational axis. So here also, first of all, what we will do, we will put this part onto a V block. This is a V block. So we will log the axis of this part and then rotate this part along the datum axis. So here it is datum A fixed at plus rotated. Okay. Now this dial indicator is moving here and in this direction. Okay. Over the length. So what is doing? The part is usually constrained with a set of V blocks or a spindle of some sort of that will constrain the part while allowing it to rotate. To measure total runout, a series of gauges must be linked to that to take care measurement in reference to each other, similar to how cylindricity is measured. Okay. So another method of measuring total runout is to take one gauge held perpendicular to the surface of the part and slowly move it across the surface of the part axially as the part is rotated. So while rotating this part, the dial indicator is moving. Okay. So in this, while dial indicator is moving, it is checking the radial variation as well as axial variation. Axial variation. Okay. So this is why it is very important that we are checking both the things in this particular uh, total runout. Okay. So this is all about total runout and the circular runout. Thank you. Thanks a lot.